Hello children, this is Ashwini from Cheenta.com. In this video, we will talk about nonlinear functions and their equations. So, I hope you have already learned about quadratic equations or linear equations. Quadratic equations are like x squared minus 3x plus 5 equal to 0. It's an example of a quadratic equation. There is one variable, x, and the highest power of the variable is 2, and it's a polynomial, so it consists only of x raised to some powers and some constant numbers. We know how to solve quadratic equations. Similarly, linear equations are 5x plus 4 equal to 20. These are examples of linear equations. The highest power of x is 1. But what about equations which contain nonlinear functions or non-polynomial functions? I'll give you an example. Look at this one. E to the power x equal to x squared minus sine x. How can we solve that? To do this, we have to gain a deeper understanding into these functions, the functions that are involved. One problem like this actually came up in ISI and BStat BMath entrance. It looked like this: e to the power x equal to sine x. How many solutions are there of this equation? I just modified it to make it a bit more fun. I just added this x squared and turned this sine x to a negative sign. This one is actually really easy, the actual problem that came up in ISI-CMI entrance. This one is a bit more challenging. We need to take a deeper dive and we need to learn more about these functions. So I'll show you how to do this. If you are new to this channel, welcome. We discuss everything related to mathematics, physics, computer science, and statistics here. We have a lot of fun with it. We have great courses on Mathematical Olympiads, ISI-CMI Entrances, Physics Olympiads, Computer Science Olympiads, and Research in School. Check the link in the description for more detail. So, how do we go about the original problem? Well, we will be drawing the graph of e to the power x, and we will be drawing the graph of sine of x on the same graph. And wherever they intersect, those will be the solutions. For those values of x, both the left-hand side and the right-hand side would be equal. That is, e to the power x will be equal to sine of x. And you will see in a moment how that looks like. You need to have an understanding about the graph of these functions. So the graph of e to the power x is like this. It's a very well-known graph. It's an exponential graph. This is e to the power x. And what is the graph of sine x? So let's draw this in red. So sine x is like so. Of course, I'm drawing a schematic picture. I'm drawing by hand, so I don't have the accurate picture here. But it's enough to give me an idea about the number of solutions. Notice wherever the red and the black line intersect each other, for example, here, here, and so on. By the way, this doesn't go up, it kind of goes down, tapers down. So I'll just use the, like this. Okay. So we see wherever this red and the black line intersects, those x values, so this is an x value, right? Some x naught. This is another x value, some x1, and so on. For these x values, if you input the x values in e to the power x and sine of x, both of them would be equal. Question is, how many such intersections are there? Well, of course, this black line goes infinitely to the left. It never touches the x equal to y equal to 0 line, that is the horizontal line, but it goes infinitely to the left. And the sine curve keeps on coming back like this. So it will keep on hitting. It will keep on hitting the black curve of e to the power x. And therefore, there are infinitely many solutions of this equation. There are infinitely many solutions. As you go to the left, more and more intersections will happen, and that would produce more and more solutions. Okay? All right. So whenever you have a nonlinear function like this, non-polynomial equation like this, you can use this strategy. Let's try the made-up version, e to the power x equal to x squared minus sine x. We'll actually learn a lot from this one. So e to the power x equal to x squared minus sine of x. Now we have to understand how the right-hand side looks like. Of course, we know the graph of e to the power x like so. We can just draw it in blue. Here we go. The graph of e to the power x. Now what about x squared minus sine x? Well, we already know the graph of x squared. X squared, I'll draw separately. It looks like this. It's a parabola opening upward. What is x squared minus sine x? So what happens is you have to understand how sine x works. So sine x here, the value of sine x can be at most 1 and at least minus 1. So between 1 and minus 1. So all that it does to x squared is that it either pushes it up by a little bit, at most by 1, or pulls it down by negative 1. Pulls it down by negative 1. So it's just the picture of x squared. It will look kind of like the picture of x squared, but a little bit pushed up, and some places it will be a little bit pulled down. Sine of 0 is 0, so 0 minus 0. So at x equal to 0, it will still be at 0. But at x equal to a little bit more than 0, it will be somewhere below, so like this, because sine of a little bit more than 0 will be something positive between 0 and 1, and it will drag down the x squared. So it's kind of like this. From a distance, it will kind of look like the x squared function, but it's just a bit wiggled. It's kind of like this maybe. Okay. Now if we draw the e to the power x function on the top of it, it will be sort of like this. Or maybe I could draw it in some other color, green. It's sort of like this. Now we have to, in this particular juncture, you have to analyze whether it will be like this or whether it will be like this. There are two possibilities. It can cut through the other arm of the x squared minus sine x, or it could sort of go up like this. So here we have to use a very important concept of growth of a function. Growth. How fast the y value is going compared to the x value. So this is related to the first derivative. The first derivative, that is the rate of change of the function with respect to y. So e to the power x, the derivative is also e to the power x, and sine x, x squared minus sine x, the derivative is 2x minus cosine of x, right? So it means that the e to the power x function, the exponential function, is growing much faster than x square minus sine x. X square minus sine x is like linear minus the sine x. So it's a little bit more or less than the linear function. But e to the power x is the exponential function. So it's growing much faster. So therefore, it is the first picture. That means it reaches, the green one, reaches greater heights far more quickly than the blue one. You see what I'm doing here, right? I'm using mathematical reasoning to solve this problem. I am using a deeper understanding about this function to solve this problem. This green function has a much faster growth than the blue function, which is x square minus sine x. The blue function is x square minus sine x, and the green function is e to the power x. Therefore, this arm will sort of spread out. So spread out, and this green thing will shoot up faster. So it will, this arm will always sort of, this distance will always diverge from each other. They will diverge from each other. So the only place they intersect is here, that they will obviously intersect, and therefore there is only one solution to this second equation. So that this equation that we have here, it has only one solution. I think it's very beautiful how you can analyze functions, analyze growths, and understand how all of this falls into one place. Thank you for joining in today. I hope you enjoyed and learned something. All the best, and I'll see you in the next one.